Good morning, everybody, and welcome to this session today of March 9th. I always tend to say February. It's not February anymore. We're in March, okay? Today, we're going to be finishing chapter 23, and Marcella had a question about the time allotted for the quiz. It's exactly how it is supposed to be, okay? So you're supposed to have a little over a minute for every question. So you're supposed to basically should be fine, okay? As long as you review the materials, you should be fine. You should not have any difficulty with it. So that was question one. The other thing also today, we're finishing actually chapter 23. And hopefully we're going to do at least one problem. One problem that looks like kind of a problem 76. We're going to do that from the 15th edition. It's problem 78 from the 14th edition, okay? I must tell you that I tested on this problem in the past, so it doesn't mean that I'm testing again, or it doesn't mean that I'm not going to be testing again. So we need to understand how to do this problem. I'll tell you also that in the past, I tested also on a problem similar to problem 72, which is not too far from problem 71, by the way. Okay. We're going to do also problem 77 from this chapter. Okay. And you know how much I'm crazy about data, so because that's what physicists do all the time. We're going to be doing problem 61 and problem 41. Those problems are actually going to be very, very useful for us when it comes time for the next chapter, which is on capacitors, okay? So we need to do those problems. Problem 46, if we can, depending, okay, it's not really, it's a number problem, so hopefully you guys can, we can do that too, I don't know, depending. And problem 57 is an important problem. I think I tested on this one in the past too on it. And that is basically the crystalline structure of salt. Basically, you have sodium on one side and chlorine on the other side. And sodium loses an electron, becomes positively charged, and chlorine takes that electron, becomes negatively charged. And now you have a crystal structure for salt, basically. And we're supposed to calculate the energy for the structure and do all kinds of fun stuff with it. So I don't know if we do 57 or not this time around, because it has applications in crystallography, or what is it? I don't know what's the word for. Anyway, it has applications in chemistry, in solid state physics, and material science. Okay, so that's why it's interesting. Problem 62 has applications actually in nuclear physics, because it talks about the Geiger-Miller counter, and that is actually an interesting problem too. I mentioned problem 81. And that has applications also in biology, because of basically how cells basically you take advantage of the voltage and all kinds of things. So the things for sure are problem 41 and 46, 76, and 77. Depending on the others, we may or basically discuss them later on, leave them for you guys to do or something like that. Okay. So that is in terms of problems. So let's finish the concept, because the concept of this topic is kind of a dry a little bit. And I know last time with you guys, we introduced the potential for a point charge. And the idea was, let me share the screen first. Unless you guys have any question right now, share. Screen, okay. Chapter 23. So basically we talked about this thing, so potential energy, the kinetic energy, and things like that. And we found the potential actually for a point charge, okay? And we invoked the superposition basically, because here is the argument. We want to understand the following question. Okay? We want to answer the following question. Where is my mouse? Does the electrostatic force, the key word in here, electrostatic. What I mean by static is this charges, when you bring them in, you bring nails with you and a hammer and fix them in place, nail them in place. They don't move, because if they do move, there's a problem. So you bring charge Q1, you bring another charge Q2, and you nail it also. So it's not moving, and so on and so forth, okay? That is going to amount to a certain energy in putting these things together, because there is a repulsion. So you really need this nail to work very hard to keep this charge Q3 from flying, okay? So So you want to keep it in a place and there and so on and so forth. So how much energy is stored in the system depends basically on this interaction between Q1 and Q2 and Q1 and Q3 and Q1 and Q1 and Q2, Q1 and Q3 and Q2 and Q3. Okay, depends on this interaction between them. That is how much energy you really need to spend to put the system together, which means that's an energy stored in the system. Because how do I know? Just let go of one of them, and it's going to convert that energy into kinetic energy. Okay, so that is basically what we're talking about in here. Does this force, electrostatic force, derive from a potential? In the 1D, it was kind of easy to work with this. In the 1D, it was kind of simple to work with this stuff because basically you write the same thing with no vectors at all. You say derive, meaning derivative with respect to x of this potential. In the case of multivariable functions, basically function in this case of the force that depends on space, x and y and z, because this whole thing is situated in a coordinate system where the x-axis and the y-axis and the z-axis are in such a way that this point has this projection in the y-axis and has this projection in the x-axis, namely x1, z1, and y1. So this was in space. Same thing with this guy. It's probably situated in this point in here in space, okay? And probably it has this projection in space in here, okay? So this is the vector R2, and this is the vector R1 for this chart, okay? So that is basically, what did I put R2? R2, oops, R2. Vector. Okay, same thing. You can think that R3 has some coordinates x, y, and z in the coordinate system. So this is actually a problem in space, not in 1D. So that's why we couldn't do this straight D, and we had to think of this function being taken derivative of in the x and y, z space. So we said that the x component is similar to this guy, with the exception I am very specific in here to fix the other two. So what that curly D in here means is that y and z are fixed. Don't worry about constants, just like 12. Think of them just like 12 or 3 or any number you would like, 60 degrees or whatever you have in your mind. X is not constant though when you do this operation. X is variable. So when you take a derivative of that function, you better take the fact that X is changing. Same thing when you're dealing with the Y component, you're going to do the same thing with respect to Y, stating explicitly in here that are implicitly that x and z are constants. X and z are the equivalent of your 12 or whatever constant you may think of, but y is not. Y is changing. Okay. Same thing in here. F in the z direction. Keep in the z direction. Sorry. Keep x and y constant, and now change just z. So that is basically, it's borrowed from this idea in a sense. But it's this idea that is actually the odd thing, because function depends on a single variable. That is odd. Function that depends on a multivariable, like space in here, is normal. Okay, that is actually the normal thing. So we get conditioned to this one as being the normal, whereas this one looks kind of strange, but it should be really the other way around. So that's basically what we're saying in here. Does this electrostatic force derive from potential? Because if it does, then if I bring a mass in here with a charge Q, then I can find its total energy. Mechanical energy will simply be its kinetical energy plus this U. Okay. I don't know if you have had this discussion about the minus in here, which is the same minus in here. Why did we put it in there? But it should have happened in such a way that minus was really needed in there so that we can write plus in here. It was just for cosmetic reasons, okay, to make things look nice, beautiful, symmetrical. Okay, so that is basically where the minus came from. So this is really the discussion that was in physics for A, with the exception of physics for A. Of course, we were dealing mainly with 1D. Namely, we found the potential energy for the spring being 1/2 of kx squared, just by integrating the force of the spring and putting minus in front of it. So there was a minus times y minus. Integral of kx gave me 1/2 of kx squared. And the potential energy for the gravity was mg times the height, in this case y, how far I am from the ground. Obviously, the integrating this function needed a constant, always that annoying thing with constants, okay? But that's really all that says is that the potential energy is defined within a constant. It doesn't say much in here. So what that means is that we're actually dealing with the difference in potential energy, not itself the energy. So what matters really in the difference of potential energy. When the power company delivers 120 volts to your plug at home, it delivers two ends. There are at least two ends in it, okay? One end is sitting at some potential. Let's say, for example, 320. The other one is sitting at 440 or 440 as volt. So that the difference between them that only matters is 120 volts. So what matters really is not how much each and every one of them is. What matters is how they differ from one another. Because one of them, you can take it as zero by choosing the constant in such a way that that constant is zero. Then the other value will be exactly the difference in potential. So if this one is zero, the other one is 120 volts. End of the story. Okay, that's it. So that is basically the trick with potential energy in general. Okay. Since we know in electrostatic that the force is equal to QE, okay, this situation, what we're saying actually is if instead of finding this potential energy, we find something so that the electric field itself derives of potential. So if E is actually equal to minus grad of V, then it could say that Q simply is QV, okay? That's it. That is all there is to it. So the energy in this situation will be QV, because if I plug back into this expression, multiply this by Q, I have U, and if I multiply this by Q, I have F. So here is how they connect to one another. The problem, though, finding then E becomes a little bit easier. If I know V, I can take its derivative with respect to Y. So it's the same thing. So EX, just replace U with V in this case, and so on and so forth, all the way to EZ, which is just minus the derivative of V with respect to Z. Again, the minus in here is needed so that this makes sense, or at least intuitively for us, that the mechanical energy is the sum of kinetic energy plus potential energy. Otherwise, we would be saying kinetic energy minus potential energy, and that is kind of imbalanced statement in a sense that we're going to have difficulty explaining that to ourselves. We argued last time that indeed for 1 point charge, we found what the potential for it is. It was actually 1 over 4 pi epsilon naught times the charge divided by R, plus that constant. What I'm saying in here, I can take that constant to be 0 in the following way. If I have a charge by itself in here, Q, and this is the distance R, by the way, this is how much potential. This is a point in space. This is not anything. There is no charge in here or anything like that. If I bring a charge from infinity, I expect in here the potential to be exactly 0. That means that far removed from the charge, I expect no effect of this charge whatsoever. I expect this charge does not influence infinity. So that is why when R goes to infinity, this is by choice, okay? The potential in this case goes to 0, okay? So if that's the case, this is basically the expression. So if I plug in R infinity, this one is 0, that means the constant is 0, that's all. Times Q over R. So this is for one charge. Now, if I have a bunch of charges, if I have another charges, we're going to invoke our friend who is, if I have charge Q1 and charge Q2 now, both of them are fixed, and I want to have the potential in here. What should we invoke? You guys remember? Our BFF in this class. Come on, guys. Who should we call?
Give me just a moment.
Okay. Okay. We're going to call on some authority.
Is it the electrostatic force?
Electrostatic force is a force, but our best friend in here to help us, basically, this is what I'm saying, okay?
The
Ignore
superposition.
superposition. Thank you very much. Have a nice day. Basically, what we're saying in here, ignore this charge completely, as if it's not there. Find the potential for this one, which is just 1 over 4 pi epsilon naught q over r1. Okay, this is the distance, what I meant by it, r1. Now, ignore this one now, and just focus on the second one. And it's going to be 1 over 4 pi epsilon naught times q over r2. Okay. By the way, these are numbers. These are not vectors. You cannot draw a vector for the potential. Just a number in that point. Okay. Like the temperature right now. In this point, for example, the temperature is so and so. But it's not a vector pointing this way or that way or anything like that. Just a number. Okay. And that location, for example, the temperature is different. So just a number. Okay. The temperature, I don't know, in Fahrenheit right now, for example, it's 68. This point is 68. It's not like a vector pointing this way or that way. No, it's just a number in that location. Okay. It has no direction. Every which way I look at it is 68. Unlike the electric field, if it's, for example, 10 Newton per Coulomb, it may be pointing in here. So if I put a charge, it's actually going to move this way. Okay. It's not going to go this way or that way or anywhere else. It's going to move this way. Okay. In that direction of the electric field. But if the temperature is 68 degrees in here, and if I bring something that is not 68 degrees, put it in here, it's going to jiggle every which way, basically indicating that its temperature has increased. Or if its temperature was high, it's going to slow down a little bit because of that temperature. Okay, that is the example of temperature in this case. Okay, so that is basically what it is. Now, since I know, again, the potential for one and the potential for the other, by superposition, the potential in this case is going to be just the sum of the different potential, 1 over 4 pi epsilon naught times the different q's over the different distances from some origin. So this is calculated at some point in space, okay? Now, if you're curious trying to find the energy, you have to be very careful with the word energy now because of the following thing. Let's say, for example, I'm trying to assemble an assembly of charges. Let's say, for example, I have Q1 by itself here. If Q1 by itself in here sitting, there is no energy associated with it because at least as far as electricity is concerned. Now, if I want to bring another charge into here and put it next to it, Q2, at this distance, which is I'm going to call R from 1 to 2, this is the distance, okay? Then I will need an energy, and this energy is clearly equal to 1 over 4 pi epsilon 2 times the potential in this point, which is Q1 over R1 to 2 times Q2. So this is an energy needed to collect these two charges next to one another. Because if I release one of them, that is going to be repelled, and that's going to convert that potential energy into kinetic energy. So this is actually the energy in the form of potential energy, because this one will be converted into the form of 1/2 mass times velocity squared. Now, if I bring a third charge, so let's say I nail this one too, after I bring it, if I bring a third charge in here that is situated, so this is my Q3 now, at a distance R13 from the first one and R23 from the second one. This charge will create a field in here that is 1 over 4 pi epsilon naught times Q2 divided by R23 times the charge Q3. Now I have actually this much additional energy between these two. Furthermore, this charge creates a field in here that is 1 over 4 pi epsilon naught times Q1 over this distance R13 times Q3. So this is how much energy for assembling 3 charges. You guys can see if I fix this charge now, if I let go of it, it's going to fly. And it's going to release this whole energy that is in it into kinetic energy. Now, if I release everything, it's going to fly every which way now, okay? And it's going to release this many joules into a form of kinetic energy. Now, if I fix this now and I bring a fourth charge in here, Q4, you guys can see the picture now. This is the distance R14. This is the distance R34. And don't forget about this distance R24. Okay, all of this distances matter now. And I have to add all of this force, this energy, and this energy. So 3 terms will be added just by adding another charge. Okay. So here is the general formula for the energy of an assembly of charge, many charges. So it's going to be the sum. None of these indices are the same because I cannot have the distance from a charge to itself. It's always from a charge to another one. So first of all, let me write that 1/4πε0. That is common to everybody. Okay, the distance between the charges I and j, where I is not equal to j. That is one thing. The product of the charges qi times qj. The summation in here is in such a way from I equals to 1 all the way to n. And so is j, by the way. But the condition in here has to be in such a way that they don't equal to one another. However, I need a factor of half, because if I don't do a factor of half, I will be doubly counting this one. I will count R12 and R21, and it's the same distance. That's why I need that factor of half. Okay, if you explore the idea initially in there and you expand that just this condition for 3 charges only, for 3 charges, n equals to 3. Here is the situation. I'm going to say I'm summing from I equals to 1 first. Okay, so I cannot have j equal to 1. So the first term is going to be 1/4πε0 times q1 for the charge 1 times q2 divided by R12 plus 1/4πε0 times q1, again I is 1 and j cannot be equal to 1, times q3 then divided by R13. So we're done with I equals to 1. How about I equals to 2? Look at the scenario I equals to 2. So I equals to 2 now will tell me that I have 1/4πε0 times now the first charge is 2 times q1, because j can be anything from 1 to 3 except not 2 in this case. So it can be 1. So it's R, again, the distance between 1 and 2. And that is exactly this term. Plus, of course, there is another term I need to account for, 1/4πε0. Again, I is equal to 2. I cannot have j equal to 2. I can have j equals to 3, though. So it's going to be q2, q3 divided by the distance between 2 and 3. Okay. Now, the last charge in here, when I is equal to 3. When I is equal to 3, j cannot be equal to 3. So I have to add to it 1/4πε0 times q3, q1 divided by the distance r between 1 and 3. And r1 and 3 is exactly this term, just as much as this term was this term, actually. Okay, so I double counted this relationship now just by doing this counting. Plus, of course, I still have one more term because j cannot be 3, so it can be 2 also. So I have to add to it 1/4πε0 times q3, q2 divided by the distance between 2 and 3, and that is actually the same term. So if I don't do that factor of half in my expression, I am double counting. So this is actually the total energy now for an assembly of charges. N charges, putting them together one next to one another. You sum from I to j, and from I to n, and you sum from j to n in such a way that I cannot be equal to j, because if you do, you're looking at the 0 distance and dividing by 0, which is nonsense. Okay, you cannot find the potential for a charge with itself. That doesn't make sense, okay? But if you do this summation, you're double counting. So you need to divide by a factor of half to find the actual energy. This is the actual energy in joules. Does this make sense? Yes? About the factor of 1/2, where we got it from? Yes or no?
Yes, I think so.
Okay, thank you very much, Andrea. Okay, anyway. Okay, very good, thank you. Okay, so basically this is how the total energy of an assembly of charges, okay? This is actually in joules, okay? So this is an actual energy. So let's go back into the potential in here. Since we found the potential for a point charge, potential for another point charge, and we know now that the electric field derives off a potential, because if it happens for one charge, it can happen for any distribution of a charge. So the electrostatic force derives of a potential, okay? So think of a way of always trying to think of V. How can we find V and to simplify life for ourselves if we can do it? So let me take an example now, which is going to be a big example. In the example, I'm going to take two parallel plates. Okay, so two parallel plates. Plate 1 is sitting in here, and plate 2 is sitting in here. These are infinite plates. They have a big area compared to the distance separation between them. This is the distance d. This is how far apart they are. And think of them as metals, if you like, okay? They are metals. So I'm going to take an electron from this charge, from this side. No, actually, I'm going to take an electron from here. So leave this one positively charged and dump it in here. So this will be negatively charged. You guys understand? So if I borrow charge in here that is negative charge, I will leave it positive in here, and this will become negative. Yes?
Yes.
Okay, so I'm going to repeat the process and continue until I have so many charges in here, Q. Of course, I will have the same Q, except it's a negative sign on the opposite side. Correct? Yes, so far? So this Q in here, since I'm doing this process again and again and again and again and again, I'm going to end up with a positive Q on one side and a negative Q on the other side, correct?
Yes.
So far,
So
so
they're
good?
they're just oppositely charged
Yes.
planes. Okay.
Yeah, so basically that is the process. I'm imagining it, okay? I'm thinking this is what I'm doing. So hopefully at the end you agree with me that at the end I will have a positive charge of some sort on one side and the same charge but a negative sign on the opposite side. So the charge distribution now then is just simply Q over A on this side. And this is a negative charge distribution. So if this is sigma, this must be negative sigma. So this is how many coulombs I dumped per unit area. This, on the other side, is actually the same charge distribution, except it's a negative sign. So far, so good, isn't it? Correct, Mundo? I don't know
Yes.
even if it's okay. Thank you. So if I go back a few chapters back, or last chapter actually, when we're doing chapter 22, we found how much electric field is produced by a plate. Okay, we found the result. This is how much it is. A plate produces, and I said the big capitals in here because it's important, produces an electric field that is sigma over 2 epsilon naught. That's all. Except one of them is positive and the other one is negative in my case. But other than that, that is how much electric field we found when we did the Gauss surface and did this analysis. If you're not sure, just go back through that derivation, basically. So I know how much electric field the positive plate will produce. It's going to produce an electric field that is sigma, pointing away from it because it's positive. Everywhere in here, it's sigma over epsilon naught. And it's pointing away from it, still here too, the same value. Sigma over 2 epsilon naught. 2 epsilon naught. I forgot the 2. I'm sorry. There is a 2 in the expression that we found last time. Okay? So that is the magnitude of the field created by that one. The other one that is negatively charged, it has a negative sigma, will produce the same electric field that has the same magnitude, sigma over 2 epsilon naught, except it's pointing toward the wire. That's all. That is what the negative sign means. So this guy will produce also a magnetic field pointing to the negative plate towards it that has the same magnitude of sigma over 2 epsilon naught. Now it's pointing towards it, not pointing away from it, okay? Each one of them has the same magnitude also of sigma over 2 epsilon naught. And in here, it's actually sigma over 2 epsilon naught. So in the red ones are actually sigma over 2 epsilon naught, pointing down toward the wire from the top and pointing up from the bottom toward the wire. And the blue ones are actually also in magnitude being sigma over 2 epsilon naught, pointing down away from the wire in the bottom and pointing up away from the wire in the top. Okay. The values are the same, except one of them is pointing toward the wire that caused it, and that's a negative, and the positive pointing away from it. So far, so good, isn't it?
Right. So for the positive charge, the arrows are going upwards for the top plate and then downwards for the bottom plates, because the blue arrows, because it
Yes.
points radially outward, right?
Yes, because it's a positive charge, always away
Okay,
from the top.
great. And then
Okay.
same with the negative charge, it points radially inward no matter where it is.
No matter where it is, it's always
Okay,
the same.
great. Okay.
That we saw last time, if you guys remember, it doesn't matter how far you are, it's always the same number, sigma over 2 epsilon naught.
Mhm.
So even if you are in here very far, this wire still produces sigma over 2 epsilon naught. Even if you are here from this blue wire, it still produces sigma over 2 epsilon naught. The only thing that matters is just the direction of the field, that's all. Because it's positive
okay.
charge, negative
So
charge.
distance doesn't matter from on the outside of the plates at all? Oh, okay.
That's fine. That's the result.
Mhm,
It's
mhm.
independent of y, independent of this number, independent of how.
Mhm.
That's what we found last time. That was kind of surprising, but needed for capacitors independent of y. That is really what we declared that the result, big deal. Okay, so that is basically what we found. Okay, let me ask you a question, you guys. How much field do I have from both plates in this region below the negative region? If one of them, the blue one, are pointing away with sigma over 2 epsilon naught, and the red one are pulling upward with the same field, sigma over 2 epsilon naught, how much do I really have in this region of total field then?
It would be 0, right? Um,
Exactly, big fat 0, no electric field outside, okay? No field. I mean, no E field, that's what I meant, no electric field. The same question, how much electric field do I have above the positive plate? The blue one is pointing away with sigma over 2 epsilon naught. The red ones are going down with the same value, sigma over 2 epsilon naught, toward their own plate. How much electric field do I have above this plate and then?
It would be the
Obvious.
same. It would be none.
Absolutely. E is equal to 0 here too. A big fat 0 too. Okay. Now I want to know how much electric field is between the two plates. Between now. The red ones are going to their own friend, which is the negative plate, down. The blue ones are going away from their plate, down. With both of them have the same magnitude, sigma over 2 epsilon naught. So how much electric field do I have inside?
it would
Would
just
it be-
be
Just
Oh.
double.
go ahead.
Well, wouldn't it be it would just be epsilon over 4. Over 4.
Plus 1/2?
Yeah. I guess it's like doubled in a sense. Well, the denominator is doubled.
Sigma over,
4.
is it 4? Or is
Am I
just,
Oh, just epsilon? Okay. Then I did it the wrong way.
okay. Do you guys agree? Matthew, are convinced? No, it's actually sigma over epsilon because you have 1/2 and 1/2 and you add them, you have a whole.
Yeah, I did the opposite of that.
How about everybody else? Justin, Andrea, Yusuf, everybody else.
Yeah,
Good?
makes sense.
Okay, so the electric field is 0 outside, above and below, and it's actually twice as much sigma over 2 epsilon naught, which is just puts it sigma over epsilon naught. So this device is useful device in a sense. If I look at it this way, let me look at it again, okay? If somehow miraculously I end up with, it has to be big plates though, so that this distance is small, okay? Otherwise that result doesn't, sigma over 2 epsilon doesn't work for a finite plate, okay? So the electric field here is 0, the electric field here is 0, and the electric field in here is sigma over epsilon naught. End of the story. So this device traps the electric field. So if you ever want to carry with you the electric field and go somewhere, camping, for example, take this device with you. Traps it between the space in between it, the two plates, because it's 0 anywhere outside, but in between, it's actually twice as much as it could be. Do you guys know what this device is called?
Isn't that just the battery?
Actually, the battery is a different, it uses chemistry. This one doesn't use chemistry at all. It uses electrostatic forces. But it's a good guess, which is actually something you take with you on camping trips too. You don't take this device with you. But actually, this device is existing with devices that you're taking with you.
Flashlight?
Flashlight uses a battery too.
Damn it.
A capacitor?
Excellent. That is the one. This is a capacitor. Okay. Let me see
Wait,
if I have
why would we take this camping?
I mean, look, you have it in your electronics, okay? I probably use the bad word in here for camping, but you have it in electronic device. You have these capacitors, okay? Because they are used actually for storing and sometimes doing the things like this one here, how it looks like. Okay. This is the device itself. I know it's too close now, you can see it, okay? So this is actually a capacitor, okay? If you open any electronics, this is how they look like. So this is a capacitor. This will play a major role for our electronics circuits and things like that. So this is the first time that you saw it. So it's useful in a sense because you can store partially energy, release energy, and do stuff in circuits with it. Okay, we didn't talk about energy, but we're going to come to it down the road in the next chapter. But it's actually for the electric potential that I need this one right now. So since E is 0 outside, I want to find the potential everywhere now. I want to find V for this device everywhere. How much is V? Okay, I know E is equal to minus the derivative of V with respect to, let's put it in a vector in general in here, of V. I know the X component, so I'm going to take the X axis in here this way and the Z axis this way. So what matters in here is actually the Z axis. I mean the Y axis. The Y axis matters because that's what the electric field changes only. It changes only in the Y direction. Since the electric field changes in the Y direction, I expect the potential to change only in the Y direction too. So the potential doesn't depend on Y and Z, depends only on, doesn't depend on X and Z, it depends only on Y. So the potential, this expression then just becomes E equals to minus dV with respect to Y, that's all. So the potential now is actually the entire derivative of the E in this case. So V must be equal to the negative of E dy, okay? Clearly E, you can clearly see that it's 0 outside, but it's a negative sigma over epsilon naught in this region because my axis, do you guys see that the electric field is negative? It's always pointing from the plus to the minus. At least if you are not convinced, just look at this picture again. You guys see that the electric field is negative, yes or no?
Yes.
Yes.
So
according to my axis, the way I drew things, it's negative. Since E is negative, then all I have to do is find the integral V from 0 to some Y of negative sigma over epsilon naught times dy. The negative cancels the negative, and I'm left with sigma over epsilon naught. And the integral over sigma, actually, this doesn't make sense. Okay, this is the entire derivative, so I don't care about this boundaries right now. So it's y plus constant. So this is the potential. It's very simple. The negative cancels the negative, and it's good. It's positive, okay? Now, for y equals to 0, which is really at the bottom plate, this is y equals to 0. I put it, this is negative sigma, this is positive sigma, and this is y equals to 0, and this is y equals to d, by the way, okay? And y can be a negative number, y can be a positive number, we don't care about that, but what I'm going to do is the following. For this special case, I'm going to say the potential in the bottom is 0. That's my choice, because it's just the coordinate system. So I'm going to choose v of 0 to be 0 by choice, okay? So that is like, for example, if I'm doing this experiment on on a surface, I can say this is where the potential energy for the gravitational potential energy is 0, not the desk, not the floor. This is where my potential energy, if I let go of it, this is how much actually converted from potential energy to kinetic energy, and it can find the velocity with which it impacts this point. If I'm trying to do it on the desk, I can take the desk to be the origin of my potential energy, gravitational potential energy, and let go and find the impact in here. I can take it to the floor. I can take it toward the planet, whatever. I can take it toward Mars if I want to, or toward the star Vega, whatever basically you want to. So in this case, in here, I chose it similar to this idea that I have in mind, which is for mg, just to take it for the lower plate. Does this make sense, this choice? It's arbitrary, really, but I'm choosing it this way. Yes?
Yeah, it does.
Okay, so if I take a, do I have my, I'm gonna bring next time around during when we do more problems, I bring my multimeter. The multimeter has two ends in it. It has the common port, which is basically the black wire, and has the red port that measures actually the voltage. So what you do in this case, you put the black one in the bottom in here. You connect it in here. That means you ground that point. You put the V equal to 0. And now wherever you put the red one, you're measuring the voltage in that point. End of the story. So that's basically what you're doing in practice in the laboratory. So that is equivalent to what I'm doing now. So if we do that, then we know V sub 0 is equal to 0. That means the constant is 0. V sub 0 is equal to sigma over epsilon naught times 0 plus constant. So this is 0 by choice. And this is 0, so the constant is 0. So the voltage in this case is going to be simply equal sigma over epsilon times y. Very simple. This is similar to what you guys did when you did physics for A, when you took a mass, for example. Let me go back in here. When you took a mass and you did the same coordinate system, the weight in this case is minus mg, because the height is what you're measuring. So you said in this case, let me find the work, and the work will turn out to be simply equal to, okay, that's fine. Hopefully, yeah, you do that too, okay? No problem. Okay, anyway, it's very important stuff, this one. There is a big important discussion point in here that is coming. So you have to pay attention to the rest, okay, of these things, okay? So if mg is pointing down, and the displacement, in this case, you're measuring the height. So you say in this case, the force is negative versus the coordinate system, and it's going to be force times displacement minus mg times the displacement dy, and you use again the same minus as part of the definition for the potential energy, and you're going to find mgy, or probably you wrote it as mgh, okay, for the gravitational potential energy. As a matter of fact, if you take a mass in here and you let go of it, it's going to lose this mgh towards its kinetic energy, that is 1/2 of mv squared. And you played with this thing a lot in physics 4a, didn't you? This is similar, except now we're doing with electrostatic. The integration is identical. Does this ring a bell to you guys, for you guys?
Yes, it does indeed.
Okay, very good. So this is exactly similar, and the y in this case is a height, just like mgh, okay? Except I don't have mg in this case. I have this kind of electrostatic. I'm dealing actually with fields. I'm not even dealing with forces at this point. If I'm really interested in the force, the potential energy in this case for a charge q, if I really bring a charge q, positive charge q in here, that charge q would be similar under a force minus sigma over epsilon naught times q. And the energy then is going to be q, it's going to be q times this number, times the potential number. So this is how much energy, q sigma over epsilon naught times y. So this is equivalent to mgh. So this has the same units as MGH, has joules also. This one is a potential, has actually the units of volts. Okay. So the units in here are in V, not in joule. But when you multiply it by Q for the charge, if you bring a positive charge, it's going to do the same thing. It's going to fall in the positive area, follow the electric field. Remember, the electric field is pointing down. So the positive charge will fall actually to the negative plate and is repelled by the positive plate. There is another problem in here with this analogy that doesn't work. So if I bring a negative charge in here in the same mixed, the negative charge actually will fall upward. So the negative charge will fall to the positive plate and will be repelled by the negative charge. So we don't really have a counterpart from physics 4A for negative charges. Although if we had negative masses, they would do the same thing. Negative masses will be stuck to the ceiling, not to the floor. Whereas in this case, positive charge will behave like masses, and negative charges, they don't have their counterpart. So if I put an electron in here, it's actually going to be moving upward, not downward. Okay, so this is basically what's going on in here. So if I have this field, because the field is raining down from positive to negative, so this is the electric field everywhere. It's pointing this way. Okay, so if I put a negative charge in there, and negative charge will be under a force that is equal to its charge, which is negative, times the electric field, which is negative in this case, sigma over epsilon naught. So the net effect is going to be Q sigma over epsilon naught. So it's going to be accelerated in the positive direction. So the force is going to be positive in the y direction. So it's going to move up. But if I bring in a positive charge, it's going to follow the field and actually go negative. The force is negative. So that is the only thing that is different. As a matter of fact, I can find the acceleration in here too. The acceleration for this charge is just divided by its mass. And now I find how much it's equivalent to G basically. And we do the same problem. So if I throw a particle in here with an initial velocity, it's going to be a projectile motion. It's going to fall, positive charge. It's going to fall to the negative plate. A negative charge will do a projectile motion, but fall to the positive plate. That is the only thing that is different in here. Okay. Now, if I draw this function for the same y, let's say, for example, this distance is 5 centimeters, just for the sake of argument. So if I come in here 1 centimeter away, so I divide it into 1, 2, 3, I divide it into more, 4, 5, 6, 7 centimeters, okay? At this level, the same centimeter, the voltage is the same. You can clearly see the voltage is the same for the same height. The same thing in here, the voltage is the same for the next height. There is a difference in potential between the first and the second, but that's another problem because this height is less than that height. So the potential in here is higher. So the potential in here is higher than the first two. The potential in here is higher than the first three, and so on and so forth. So these lines in here that have the same potential are what we call equipotential surfaces, because this thing extends to the screen. Okay, I'm not drawing. I'm saying a surface A, but I'm drawing a line because that surface extends toward the inside of the screen. Same thing, these lines are also surfaces extending to the lines of the screen. So these green surfaces are what I'm calling equipotential. I don't know if I'm spelling this right. Surfaces. Equi meaning the same surfaces. You can clearly see from this region in here that the equipotential surfaces are in the x direction and z direction, whereas the electric field is in the y direction. So you can visualize this as follows. For this one, if this were an equipotential surface, this is an equipotential surface. What I mean by equipotential, I think I messed up that. Did I put an A in there? That's bad. That's an E. E-N, okay? So an equipotential surface, that means this entire region has the same voltage. If I bring a voltmeter and put the red in here, and if this were, for example, 2 volts, it's going to read 2 volts everywhere. So wherever I put it is the same potential. The electric field in this case is perpendicular to it. The electric field is actually in the z direction. I mean, in the y direction. So this is E pointing in the y direction, whereas this equipotential clearly is in the x direction and the z direction. So this is the x direction and this is the z direction. So it looks like the electric field and the equipotential surfaces are perpendicular to one another. Is this true only for the case of this parallel plates, or is it true all the time? Let's try to answer that question. Okay. Is this unique to parallel surfaces? So how are equipotential surfaces related to the direction of the electric field? This is a big deal, okay? We want to find this result. We found them perpendicular in this case. Is this true only for this case, or is it true all the time? So let me take an arbitrary equipotential surface. What I mean by an equipotential surface is a surface that has an arbitrary shape in here. This is a surface, not a line, by the way, where the electric potential in here is the same as this point, is the same as that point. So for example, you measured 7 volt in here. This is actually also 7 volt, and this is 7 volt, and it's 7 volt everywhere on the entire surface, whatever its shape is, okay? And I want to know the direction, or at least the electric field, how is it related to this one? Its direction, at least. So let me, when I say 7 volt is with respect to some origin. So for example, this is 0 volt. So this point in here could be 7 volt. This point in here, the difference is 7 volt, and the difference between this point and that point. So the COM port from the for the voltmeter is sitting in here, and when you change the red one in every point on the surface, it's always reading the same thing. That's what I mean by 7 volt. Okay, so with respect to some origin somewhere. Okay, so let's look at when we move on the surface. So I'm going to go on this point in here on the surface and move next to it, a distance delta r. Okay, so the displacement, now we are on the same surface, and we want to find how the electric field is related to that. I know that EDR in general with a minus sign is equal to the change in the potential, or the difference in potential, the potential itself from one point to some reference. So if I go from point 1 to point 2 on this graph that are separated by delta r, I'm going to expect that this is the difference between this point potential and that potential. But this is an equipotential. By definition, there is no difference in potential. So the difference between these 2 points is 0, because both points belong to the same equipotential. By definition, an equipotential is the voltage is the same everywhere. So if you're trying to find the difference in potential between one point and the next point, it's going to be 0. So now this spacing between the 2 points is small enough so that E is more or less uniform. E is uniform over the distance delta r. So the 2 points are close enough so that E comes out of the integral. So this basically is just basically E times delta r with a negative sign if you care, because it's 0, it doesn't matter. So the product of these two vectors is 0. Either the electric field is 0, and that is actually not what we're interested in. That's a trivial case. Or delta r is 0, but that's not the case because we're looking at 2 different points on the same surface. So the other option is these two vectors are perpendicular to one another. So the electric field in here, if it exists, it's perpendicular to this region. If it's pointing this way, or if it's pointing in the other region, it's perpendicular. So the electric field is perpendicular to this point all the time, no matter which way you look at it. So if it's in here, it's going to point this way, so that this angle is a 90-degree angle. So the electric field is going to be perpendicular. If I multiply this vector by this vector, it's going to be 0 because cosine of 90 degrees 0. So that means E is perpendicular to delta r, no matter where on the surface. Obviously, if I move from this point to a next point that is outside of the surface, this difference is not 0, and the dot product is not 0. So they may not be perpendicular. But on the equipotential itself, since I'm on the surface itself, moving from one point to the other, there is no difference in potential between those 2 points by definition. That's exactly what I mean by an equipotential. So in this case, the dot product of this vector by delta r by any distance over the surface itself is 0, meaning that these 2 vectors are perpendicular in general. So this is not unique to this situation. It's true all the time. okay? So here is the deal now. This is the item of the discussion that I want you to really think about it, because it's crucial. This is what helps you find the electric field practically in the lab. Not with calculations, not with those nonsense stuff, curly derivative, partial derivative, and things like that. Probably ideal situations that is very hard to do in the lab anyway. It's probably not even possible to do in the lab. So how can we do it in the lab? You take a voltmeter, okay, multimeter device, and hunt for where the voltage is the same. Let's start with this point, for example. This is my origin. This is where the COM port is. So this is a 0 volt. And you look around in here. Let's say, for example, I found 1 volt. Look in this region surrounding it. Look for another 1 volt. Let's say I found it in here. That's another 1 volt. Okay. Moved up, it's more than 1 volt. Moved down, it's less than 1 volt. So this is actually the exact point in here. So I'm looking with the red one, trying to find where the next 1 volt is. Don't move this one though. This one is nailed now. This is 0. You cannot move that because you're finding the difference between this and that. Now, found this point, again, another 1 volt. And go around connecting this point. For example, this is my equipotential. Of course, it's a surface. I'm drawing it as a line in here. So that's my equipotential. And let's look, for example, where the 2 volt resides. Let's say, for example, we find the 2 volts in here. So this is 2 volt. This is actually 2 volts, and connect the 2 volts. Let's say, for example, this is how it looks like. So this is a 2 volt. Look for the 3 volt. The 3 volt was here. Then there is another one in here. Then I looked around and I found it to be here. I'm sorry, I went through the other side, which is possible, but going to be a problem if its distribution means it's non-uniform. Okay, it's very close in here, not exactly contact, but it's very close. So now I have the equipotential surfaces. I can draw the perpendicular here, and I know the electric field is here, pointing this way. I'm sorry, I drew it in the wrong direction. Never mind, this is wrong. The potential is increasing in this direction. So that means the electric field is pointing away from the decreasing. So it's actually pointing here. And it's perpendicular, and it was here. So this is a 90-degree angle, this is a 90-degree angle, and this is a 90-degree angle, okay? So because it points from high to low all the time. So for example, it's pointing this way, that's supposed to be 90 degrees. It's supposed to be like this, that's a 90 degrees. And by the time I reach this point, it's pointing this way. So again, it's from high to low, from 3 to 2 to 1 to 0, always. So I know its direction just by finding the potential. I can find it if I find the equipotential by drawing the perpendicular. I can find its strength too. Where it's changing rapidly, remember the electric field is related to the rate at which V changes with time, with not with time, with space, okay? With a minus in front of it. So where this change is big over a small distance, the electric field is strong in here. Where this change, this is from this point to this point, where this change from this point to this point is basically doesn't change much because this entire region is from 2 volt to 1 volt. Doesn't change much at all. So in this case, the electric field is small because this ratio is actually small. Over this big delta X, the same 1 volt drop was much higher between this point and this point, which are very close from one another, versus from this point to that point. So this tells me a lot. It tells me about the direction of the electric field. Drawing the equipotential tells me everything about the electric potential. It tells me about its direction. First of all, from high to low. End of the story. Second, it tells me in every point which way it points. It has to be perpendicular to the equipotential, number 2. Number 3, it tells me the strength if I look between 2 equipotential regions. Just like when you do the velocity, for example, which is the ratio of the distance traveled over amount of time. So you do one measurement now for the position and another measurement later on for the position, and take the ticking of the clock in the first measurement versus the second one, take the difference in displacement divided by the difference in time, and that is your velocity, how fast you're moving. If your space doesn't change much over the same time, that means You didn't hardly basically changing your velocity in this case, it's constant. And I'm sorry, I probably gave the bad example in this case. Let's say, for example, I'm looking at 1 volt separation, 1 second separation, and you cover a lot of ground versus small ground in this case. So the distance in this case is 1 meter. So you went from 3 meters to 2 meters to 1 meter. So basically the spacing is this much always. But in here, it took you 1 second to do that. Whereas in here, it took you 10 seconds to do the same meter. So it's 1 meter and it's still 1 meter. The velocity in this case is 1 meter per second. Whereas in here, it's 1 meter per 10 seconds or 0.1 meter per second. Obviously, you're going slower for the same distance, taking longer time to do it than the same distance over the shorter period of time. This is similar, except rate in space now. How much the potential changing? Change from 3 volt to 2 volt over this big space in here. That means the electric field is weak in that region. Whereas it took a lot less distance to change the same voltage from 3 volt to 2 volt. Okay, so this is the analogy with it, except now this rate is not in time. This rate is actually in space. So it tells me everything I need to know about the electric field. So forget about all of the calculus, forget about the curly and all of that. This is the main topic of chapter 23. This is the main idea. This is really what I want you guys to come up with, how to find an electric field if you know the electric potential. And the idea behind it is the following. Find the equipotential surfaces. From the high voltage to the low voltage is the overall direction of the electric field, number 1. Number 2, where the gradient is the highest is where the electric field is the strongest. This is what I mean by the gradient. This ratio, basically. When the gradient is the highest, the electric field is the strongest. And furthermore, the electric field is perpendicular to the equipotential surfaces. Make sense to you guys?
Yes. Yeah.
Yep.
This is from practical perspective. You are an experimentalist physicist who doesn't care about the theory that much, doesn't care about all of this curly stuff and partial derivatives, which don't amount to a lot when you're doing the lab. This is how you do it. We used to do this lab, and it's a lot of fun when we do it in class, by the way. You take basically conducting papers, you put conducting materials on it, you connect one end to a power source, you connect to the other end to another power source. Basically, one of them, both of them to the same power source. One of them is set as specific voltage, the other one is different voltage, then the voltmeter. Now you start hunting for your equipotentials. Once you find them, you draw the electric field manually. It's a lot of fun. Unfortunately, now we cannot meet to do this lab, but that's really the heart of this topic, okay? We still have a very, very important topic that we're not gonna cover right now, but next time when we meet, and that is a dipole, okay? And still have about half an hour, actually a little less than that, to do problem 76. Are you guys in the mood for it? Yes or no?
Answer?
Sorry?
I said, do you want our honest answer?
Yes. Yes. Do you want to do problem 76 or not?
Let's do it.
Okay, thank you. Thank you very much. You said no, I will go. I'm going to do it anyway. Okay.
You're
Because I
gonna
think
what?
it's-
I'm sorry?
I was going to do it anyway because I think it's
Oh
important.
yeah, you see, so even with or without our honest answer, we were gonna have to do it.
I think it's important. I think you will enjoy it too. I think because we can do theory all day long, and if we don't really see problems, how they are worked and how you can tackle them, and when you're facing them for the first time, they might be a daunting task. They might be hard to even start with them. So this is really to basically make them approachable in a sense. Make sense?
Yes.
Make sense or not? Okay,
I
very good. Thank
100% agree with that.
Very good. So, problem 76, and I think it's problem 78 from chapter 14. So if you have chapter 14, from the 14th edition, okay? So what it tells you in here, it gives you a potential. By the way, I tested on this problem in the past, okay? Something like this one. So it gives you a potential, and this potential is clearly a multivariable function, okay? And it tells you specifically that it has this A, which is a constant, depends on X in the fashion that is X squared minus 3y squared plus Z squared. And this is basically the potential, okay? Where A is constant, good. Otherwise, we have a problem if it's not constant, okay? And they tell you derive an expression for the electric field at any point in this region. So we want the electric field E. Okay. So the electric field is equal to E minus grad of V. Or if you want to write it symbolically, I mean, this is symbolically, if you want to write it explicitly, so it's a derivative with respect to X, the derivative of V with respect to Z, and the derivative of V with respect, I'm sorry, Y, and then with respect to Z. Be careful here about this vector. Okay, so EX, the component of the electric field in the X direction is minus, don't forget the minus, okay? This is when some of you guys lose points when we're doing exams, okay? So there is a minus in the definition, okay? And again, this is a cosmetic definition that is critical later on for your analysis. Otherwise, the masses will fall to the higher potential, and that doesn't make sense, okay? Always fall from high to low. That is really the minuses. There is nothing wrong if we admitted a convention that they fall from low to high, but it goes counterintuitive, basically, language. They always from high to low. That's why we put the minus in there for cosmetics, basically, so that people are not confused, okay? So Y is constant. It's just like 12 in this case. Z is constant, just like 12, and X is variable. So I'm dealing with the derivative of X squared. What in the world is the derivative of X squared?
2x.
Very good. That's easy enough. So easy that even I can do this. Yes.
Yes.
You're a physics major.
No, my point in here is that this is something that you guys can handle from your CAD classes. So this is not hard.
Professor, let me just say, very
Sorry?
good. I'm saying, like, congratulations to you, because I don't think I could ever be a physics major. Too much math.
Believe me, it's a lot of fun if you enjoy it, okay? So that's really the point for it, okay? If you don't like something, you can't do it. Anyway, the point being in here, let's do the second one. Minus times minus is going to be a positive, so you have to pay attention to that. 2 times y, 2 times 3 is 6, times a times y. Everything else is constant. X is constant, z is constant when you're doing this one. That is what curly means. Does this make sense to you guys? That first of all, it's positive, and it's 6a times y. You guys see the connection?
Yes.
Okay. Absolutely. You guys really need to pay attention because this is a very simple example and it's really meticulous. All of the other stuff really is the same thing. So when you're dealing, I know that probably some of you did not do multivariable calculus yet, but when time comes to it, it becomes so trivial. As a matter of fact, it becomes easy at the end. It becomes really, how could I have survived without it, really? So EZ, in this case, is going to be exactly like EX, except that X is replaced by Z because this function depends on X as much as it depends on Z in the same fashion. So there is a 2Z, A. These two guys are constant now when we do that. So we have answered part A of the problem. This is how the electric field look like. Because I expressed it in terms of EX, EY, EZ, and that's how it is. So if you're really curious trying to write it as a vector, you can write it as a vector. So if you want to write it E as minus 2AX I hat plus 6A y j hat minus 2az k hat, that's the same thing, okay? Writing it either in its component or writing it in terms of the xyz component, coordinate system is the same thing. So at this point, we have answered part A. Part B, the work done by the field when a 1.5 microcoulomb test charge moves from, so basically, let's look at this question. Always when you're reading, write stuff, okay? So part B, they gave us a charge Q of 1.5 microcoulomb. That's one thing. And they tell us this charge moves from this point of coordinates X, Y, Z that are equal to 0, 0, and 0.25 meters. 25 centimeters basically, down to x, y, z equal to the origin. And the origin has coordinates, of course, 0, 0, 0. That is what the origin is. So this charge moves from here to here. And it moves in such a way, we need to find basically we have the potential already. Here is the potential. So we have the potential V, first of all, in the higher point. V, I'm going to call this point 1, and I'm going to call this one point 2. Okay, so we have V1, the potential to start with, was equal to A times 0 squared minus 3 0 squared plus, here is the expression I'm subbing in it, plus 0.25 squared. Okay, if you write it explicitly, 0.25 is 1/4, so it's A squared over 16. I mean, no, there is no such a thing, A squared. A over 16, makes sense? Because this is 1/4 squared, so basically A over 16. Volts of some sort, so this is volts. Now V2 is equal to A times 0 squared minus 3 times 0 squared plus 0 squared, so it's 0 volts. So it went from A over 16 down to 6 volts, okay? So there is a positive number in here down to this 0 volts. That is how much basically it fell, and it's a positive charge. So the work in here is the work of the force of gravity, basically, like when the mass falls from high to low. So the work in this case is going to be the charge times the difference in potential. It's going to be V1 minus V2. As a matter of fact, I could write it as minus Q times U, because the work is actually the force times displacement. So the work is actually FdR summed up, whereas the potential is minus FdR. Okay, so there is a minus between them. So it's actually is going to be Q V1 minus V2. It's usually, we write it to work as U1 minus U2. We don't write it, again, that minus thing in there, okay? So when we move to the other side, the conservation of energy is basically here. You guys remember this theorem from your discussion from your physics 4A?
Yeah, it looks familiar.
Okay, so that is basically the work. It's U1 minus U2. And in this case, it's going to be Q. Q, they tell us specifically, is 1.5 microcoulomb times V1, which is A over 16, minus 0. This, they tell us the work is how much? The work W they gave us, that's part of the problem, is 6 times 10 to the negative 5 joules. So this number is equal to 6 times 10 to the negative 5 joules, or 60 microjoules, because micro has 10 to the negative 6. That's why I put the micro in here, because I see a micro in here. So when you see a micro and a micro, it's a good idea to introduce them so that you can get rid of them. So this micro and that micro will cancel. And I will be left with A divided by 16 times 1.5 is equal to 60. Okay, hopefully you guys saw where this number came from. This is the micro cancels the microjoule, so the powers are gone. If you're not convinced with this approach, just basically keep the powers and get rid of them at the end. Don't forget that the micro is 10 to the negative 6. That's all. So at the end, I have an expression for A. So A is equal to 16 times 60 divided by 1.5. 1.5, so this is 600 divided by 15. 60 divided by 15 is 4. And 4 times 16 is 64. So this is 640, the units now. The units has to be volt per meter squared, because of the fact that I'm multiplying this A by a meter squared, then a meter squared, then a meter squared to get a volt. So A better have this units of volt per meter squared. Make sense of how I got this number?
Yes, but Professor, I have a question. So in the beginning, the problem was asking for the electric field, or the...
Yes. Yeah, here it is.
Okay, and normally when we're finding but we don't have 2 points. Never mind. Okay, that makes sense. So what you did was you distributed it out, and then towards the end, you plugged in the numbers to find the work done. And the work
Yes.
done was our volts per
Yeah.
meter.
Okay, hold on. So basically, this is what we know. The problem says the following, that you have a charge. You bring a charge now. It has
Mhm.
nothing to do with anything. You bring a charge of 1.5 microcoulomb, and you measure how much work is done to go from this point to this point. So I want to find this work, first of all, in terms of the potential. The work is, the potential energy is Q times V. The potential energy in joules is Q times V. So as I have V, I have to multiply it by Q, which is 1.5 microcoulomb. The difference in potential energy is the work.
Okay.
And the work, they gave us the work. They tell us it's actually 60 microjoules to do that. So now the only unknown in this equation is A, because we don't know what that A is. This is part of how we found A actually. So now we know A, so we know what the potential is. So if you want me to write the potential again, so the potential V is going to be 640 times x squared minus 3y squared plus z squared. Where this 640 is actually in volt per meter squared, where you cancel this meter squared for all of these units. So now we know A. Make sense?
Yeah, that makes sense. The math
Okay.
made sense. I was just like, wait, but yeah, now that you explained it, I saw that it was, yeah, it makes sense. It's complicated, but it makes sense.
Okay, here is the deal. What you need to remember is that the potential energy is QV. Okay, because the force is equal to QE. Okay, and F is equal to minus grad in general of U, and E is equal to minus grad of V. So all of this relationship are connected to one another. Okay, so this is very important in here. This guy is in joule, this guy is in volt. Okay, this guy is in Newton, this guy is in Newton per coulomb. This guy is in Newton, this guy is basically joule per meter and so on. As a matter of fact, let me do something in here, very, very critical, okay? The electric field, because of its definition this way, the units for the electric field are going to be the units for the volt, for the potential, which is volt, divided by meter, because when you take the derivative, you're dividing by delta x or delta y or delta z. So the units are volt per meter. From now on, we are not going to be using Newton over Coulomb for the unit of the electric field, E, but rather we're going to be using volt over meter, which are the same units, but it's more common to use volt over meter. So from this point on, I want you guys to forget about Newton over Coulomb for the unit of the electric field, but rather use this definition for the potential as the volts over meter. Is everybody okay with this point from this point on? Because this is item 2 of the discussion. From this point on, we're going to be using the units for the electric field as volt over meter, not Newton per Coulomb. Good?
Yeah.
Okay, so please remember that, because sometimes it's confusing. You see the units, it doesn't make sense, but that's why it's volt per meter, okay? Volt over meter. Now determine determine the electric field at that point 1, 0, 0.25. They want the electric field in that position. Okay, since we want the electric field, we have its x component, which is minus 2a times x, and x is 0. So the electric field in the x direction is going to be 0. The electric field in the y direction, the component in the y direction is going to be 6 times a, which is 640, times 0, which is going to be 0. And the electric field in the z direction is going to be negative 2 times a, which is 640, times z, and z is 0.25. So basically, the electric field, that's part C, E in 0.1. Remember, 0.1 has a definition of 0.25 meters. So the electric field, remember, in the x direction, if you plug in the equation, it's going to be 0. The y component is going to be 0 because x and y are 0. But the z component is going to be minus 2 times a, which is 640, times 0.25. And that is half of, because 0.25 times 2 is 0.5 times 640, that's about negative 320 volt per meter. Okay, remember A has the units of volt per meter squared, and this is meter, So this is why I was saying the units for the voltage are going to be this thing in here. So the electric field is pointing down in the z direction. Okay, and 0 at the other 2 points in that point. Okay, and that's why it was a higher potential. Remember, and the charge that was positive 1.5 microcoulomb moved from the high potential to the low potential where there is 0 potential. Okay, it moved from a point where the potential was, what is it? This potential A over 16 down to 0. If you want to divide 640 by 16, it was moved from 40 volt down to 0, basically. And the reason why the electric field is pointing in that direction, pointing from that point to 0, which means it's negative. And the point is above the axis, by the way. The point is here. So here, let me draw this picture here so that you guys see it, okay? So here is the x-axis, here is the y-axis, and here is the z-axis. The point is here. This distance from here to here is 0.25, quarter of a meter, 25 centimeters, okay? The electric field is pointing this way. And the charge that I put in here, 1.5 microcoulomb, moved from here to there, because this is where the origin of the axis is, okay? The voltage actually here, if I computed, was 40 volt, okay? So in here, it was 0 volt. And that's why the charge moved there. Make sense now the problem? Because you put a positive charge, it's going to follow the direction of the electric field. It's going to go down. If it was negative, it's going to move in the opposite direction. Still have about 3 minutes, and we have 2 or 3 questions I want to hit them before we end. Is that okay with you guys?
Yes, that's fine.
Okay, thank you. So basically, we found the electric field in the right direction. That is critical. So in your discussion, you really have to think about these things, what's going on. D, show that in every plane parallel to the XZ plane, the equipotential contours are circled. Here is what question D is saying. Show that in every plane parallel to the XZ plane. Let me draw that graph to see what the XZ plane look like. So this is the x-axis, this is the z-axis, and this is the y-axis. This plane is the XZ plane. If I move a distance y naught, that too is parallel to this plane. So the planes that are parallel to the XZ plane have the same y. Y is the same everywhere on this plane. Y is 0 on this plane. But y could be any number you like. It could be 10 for that matter. And it's, as long as it's 10 everywhere, that is a plane that is also parallel to the XZ plane. So y is fixed on those planes. So I'm going to write it as y naught. And v is an equipotential, so it's constant too. So v, if you guys remember, is equal to 640 times x squared minus 3y naught squared plus z squared. Remember, this is fixed. This is means parallel. This is the definition of a plane parallel to XZ plane. Now this is constant. I'm going to move it to the other side, and I'm going to end up with the following scenario in here. First of all, v divided by 640. When I move a negative number to the other side of the side, what happened to its sign? Comes positive, doesn't it? 3y naught is equal to x squared plus z squared. Does this make sense, this equation? Squared in here. Yes? I divided 6 by 640 and basically plugged in everything in here, correct? Yes or no? It's an algebra.
Yep.
Okay. Because y is constant. That's by definition what an XYZ plane is. So obviously this is the equation of a circle that is centered in x equal to 0 and z equal to 0. That is the center of the circle. And the radius of the circle is this number under the square root. So the radius of the circle is v over 640 plus 3 y naught squared. Okay, so this is the point. The equipotential means V is constant. The equipotentials are actually part of circle. They are circular shapes of this radii. So this is the radius of all of the circles. This is plus, by the way. Okay. So this is what this is. So they're centered around 0, 0, and this is their radii. If you increase V, the circle increases. If you reduce V, the circle reduces. If you go from high to low, depending on where you are on the X, Y axis, again, the circle changes radius, that's all. But it's a circle nonetheless, as long as you stay on the X, Z plane or one of its parallel planes, up and down. So that answers the question. Does this make sense to you guys?
Yes.
Okay, so what is the radius of the equipotential contour corresponding to V equal to 1280, and also Y is equal to 2 meters. So Y naught is equal to 2 meters. That's the last question in here. That's question, what is it? E. And V is equal to 1280. 1280 happened to be exactly twice this number. Isn't this coincidence? 1280 divided by 640, that's 2. Plus 3 times 2 squared, which is 4. So I end up with 12 plus 4. So that's square root of 14. Square root of 14 is more than 3, but less than 4. So it's going to be 3 something meters. It's going to be probably 3.7 meters, okay? Because it's close to 16, but far more than 9. It's a good idea to plug this number in the calculator and see exactly what this number is. Square root of 14. 3.74. Okay. 3.74 meters. So this is for 1,280 volt at 2 meters away from it. That is the equipotential in this case. That surface in there will give me the voltage. So if I have the voltmeter sitting at 0, that's where the volt 0, 0, by the way, you found it. And the black one, the COM port. And the other one, if I go around and find 1,280 volt, I go around the circle whose radius is 3.74 meters away from the coordinates x0 and y0 and 2. So here is how that contour looks like. This is x, this is z. This is x, and this is y. So this is my 0 volts, by the way. That's where also the 0 origin is too, okay, for the x-axis and everything. So if I go 2 meters above, I have to go 3 meters in here, almost 4 meters, 3.74 meters, okay? And look in here, the voltage around this circle is all going to read the same thing, 1,280 volt everywhere. So that is my equipotential surface in here. Okay? Makes sense to you guys? Or actually contour, I'm sorry. Does this problem make sense to you guys?
Yes.
Yes, it does.
Okay. This is problem 76. Hopefully you guys practice with these things and understand them. When we meet on Thursday, we have that idea first for the dipole that I promised a long, long time ago that we're going to do. And then we're going to do problems 41, 61, and 77 for sure. And depending on the time and everything else and what we feel we do, problem 46, problem 57, problem 62, and problem 72, which I will tell you up front, we're not going to be able to do all of them, but at least hopefully some ideas from them, okay, from one of them or two. Okay, I see you guys Thursday.
Alrighty then.
Thanks, Professor.
No
Yep.
problem. Thank you, guys.
I have a quick question about the book actually. Since you're saying these prompts on like, is this for the 14th edition? Is this correct?
This is actually the problems, all of them are from the 15th edition, but if you happen to have this 14th edition, you will have them numbered differently. Now, if you have problem that is missing, please let me know and I can give you the wording of the problem because.
Yeah, just because I'm using the like e-text and I have the 15th edition, you know, of the whole like theme, but
This is So you don't have a problem.
Well, I just can't find it. When you say these problems, like I don't even know where they are.
Wow, that's the problem. Why is that? You have, what do you mean? You have a PDF version or what is it?
Yeah, well, it's the e-text version of it, of the, like, you know, the whole thing. And
On Master of Physics.
yeah, should I like not use that?
That's the one. Yeah, let me go into the session here, my session.
So I was looking this whole time and I was like, okay, I can't find it. I'll just write what you're saying.
Okay, let me log into mine. Master of Physics, actually. Master, yeah. Come on. If for some reason you cannot find it, that's a good thing to contact the publisher and tell them about it.
Okay, for what was the problem that like we did? I think I see where it is.
Okay, problem 76 from
Okay.
page 778. Okay.
So yeah, it says I see this. It says a helium nucleus is known as an alpha particle, consists of like protons. I see this, but I'm not sure if that's the same.
I found it, but it's under questions, exercises, problems
Yeah.
for chapter 23.
Problem 73?
76.
76. Okay,
Yeah, it's under
electric.
chapter.
Oh, okay, I see it now. Okay, this makes sense. I was so lost. I followed along, you know, with what you said, just I didn't have the wording in front of me. This makes
Yeah,
sense.
if you go to problems, questions and problems, and actually probably a quick way of doing it and a dirty way of doing it. Why am I doing chapter 1? Man, I'm doing chapter 1. Okay, so let me go back into it.
This
I don't
makes
want.
sense now. Which were the problems that we're going to cover later, so I can, you know, kind of have like a preview of it when we come to class?
Problem 41, 61, and 77.
77 of chapter 23, correct?
Yes.
Okay, perfect. Yeah, I'll take a look at these. And... Perfect.
Okay.
Cool. Have a good one.
You too. Thank you. Bye.